Well, hi everyone, and welcome to Algebra 2, Section 5.1, Monomial and Ponomial Review. It was kind of faded there in the section title. That's what it's supposed to say. A monomial, mono meaning one, is a number, variable, or product of numbers and variables. Notice a, singular. So some examples could be just the number 4, or the variable x, or the product 7x, or like 3x squared y, for example. Those are all monomials. Features of monomials is that there's no addition or subtraction, essentially, as well as there is no variable in the denominator. So once again, some non-examples would be like 3x plus 5. The addition sign makes it not a monomial, as well as 3 over x, the variable being the denominator. It'd be fine if it was like x over 3. That is a monomial because the denominator is not a variable. Moving on, we have some exponent rules that we're going to remind you of. Remind because we've been working with them this year in Algebra 2, as well as learned them back in Algebra 1. So the product rule deals with when you multiply two bases. Bases is what's raised to a power. So a to the power of mth to the a to the power of n, or excuse me, a to the mth power and a to the nth power, or to the power of m and n. So two bases are the same. So this is the same base, whether it's 2 or 4 or 8 or any number or any variable. And what you would do here is you then add the exponents. So you do m plus n. So an example here would be that if you have x squared times x to the 7th, this gives you x to the 9th. Next, the power rule. So if I were to have some variable or some base a raised to the power of m, and outside the parentheses that is raised to the power of n. Well, this ends up becoming a to the power of m times n. We multiply the exponents together. And the same thing is true if you have multiple things inside that parenthesis. And so, for example, here, if I were to have x to the power of 2 to the power of 7, we multiply 2 times 7 and get x to the power of 14. The quotient rule means that you divide the bases. So a over a, but the top one, let's say, is the power of m, and the bottom one is the power of n. You would subtract these exponents, power of m minus n. So for example, if we had x to the power of 7 over x to the power of 2, we do 7 minus 2 is x to the power of 5. Now note, on each of these, the bases are the same. So a, x, x. This does not work. You cannot do these rules if they're different bases, such as x and y, or 2 and 5. Negative exponent rule. So any negative exponent just tells us that the base needs to be reciprocated. So a to the power of negative m equals 1 over a to the m. Additionally, if I had 1 over a to the power of negative m, it's on the bottom of the fraction, then that reciprocates as well to the top. So if it's on the top, it goes to the bottom. If it's on the bottom, it goes to the top. And so example of this would be like x to the power of negative 2. This is 1 over x squared. Now note that the base stay the same, the number for the exponent stayed the same, but the sign and location change. The sign of the exponent and the location of the base and exponent change. And then last but not least, the zero exponent rule. And this is that anything raised to the power of 0 equals 1. It is important to note here that 0 to the power of 0 is undefined. Similar to how dividing by 0 is undefined. It breaks math. So for example, if I have 7x to the power of 2 all raised to the power of 0, this just becomes 1. Literally anything raised to the power of 0, other than 0, is 1. So let's go ahead and apply this. So when adding or subtracting monomials, we combine like terms. But when we multiply, you just multiply similar things together. So you multiply numbers together using the same rules we've used for multiplying numbers together since elementary school. And then when we multiply the bases, so here like x and x, for example, then we deal with adding those exponents and those exponent rules that we mentioned above. So here on number 1, when I have 5x squared times negative 7x to the 6, I say 5 times negative 7 is negative 35. I tried writing that with my pencil, but it didn't quite work. And then x squared times x to the 6th gives us x to the 8th. Add those exponents. And that's our answer. Number 2 here, we have a little bit more going on where we have this exponent outside here. So we can't just multiply straight away and do negative 2 times 8 because the order of operations says that this exponent takes precedence or comes before this multiplication. So what I have to do is multiply this exponent of 2 to everything inside. Secretly, this negative 2 has an exponent, and that's what we multiply with. We do not and never will multiply exponents times bases, aka 2 times a, or 2 times 2 here in the scenario. That only happens in calculus at a very specific time, and this is not calculus, this is algebra 2. So we say negative 2 to the second power, important that we note that that is in parentheses, a to the 6 and b squared. This was secretly a 1 as well. And so negative 2 to the second power is really 4. So this becomes 4a to the 6 b squared. Let me rewrite that 6. And this 8a to the b to the 9th just kind of was hanging out and chilling. All right, and now we multiply it together and do 4 times 8 is 32. A to the 6th and a to the 1st give us a to the 7th when we add those exponents. And b to the 2nd and b to the 9th give us b to the 11th. And so we get 32, a to the 7th, b to the 11th. Moving on to number 3. Once again, we have something taking precedence before subtraction here, or before addition on the previous problem and subtraction on this problem, and that's division. So we divide things just like we've been dividing since elementary school for the numbers, and then we deal with the variables and exponents the same way we have the rules above. So 54 divided by 3 is 18, and then 6 minus 2, since they are both the same base m, it gives us m to the 4th. And 4 minus 1 on those powers of n give us n to the 3rd. And this is subtracting 10m to the 4th, n to the 3rd. Now, a reminder that we cannot subtract or add these unless they're like terms. And in order to be like terms, these have to have the same combination of variables and exponents on those variables. They do have that same combination, so they are like terms, and thus we can subtract. So we do the coefficients. 18 minus 10 gives us 8, and we leave the variables and exponents the exact same as when we started. We only change variables and exponents when we multiply and divide, not for addition and subtraction. Number 4 here. So there's a couple ways this can be approached, and I'll talk about each way this can be approached. So first and foremost, we have multiplication. I see 2 times 10. I can get that to be 20. I'll try that again. 20. And then k to the 4th and k to the negative 7th. I add those exponents and get k to the power of negative 3. Now, I'm not done here yet because I don't want negative exponents as part of my answer. So I need to say this is 20 over k to the 3rd. This 20 does not have a negative exponent. This 20 has an exponent of positive 1. So it stays where it is. The only thing that moves are those things that have negative exponents. In this case, just the k. So only the k moves, and so k to the 3rd is now in the denominator and positive exponents. And this is our answer. Now, another way you could have approached this problem initially would have been to say, this is really 2k to the 4th staying the same over, times 10 over k to the 7th. And take this, k to the negative 7th, and reciprocate it or put it on the bottom right away. That's certainly an option as well. And how you would go about this then is you say 2 times 10 is 20, just like before. And k to the 4th times k to the 7th. Now there's actually 2 ways to approach this. So one of the ways is saying 4 minus 7 is negative 3. And so we end up having k to the negative 3, which we know that results to this, like we saw right here. The other way to approach that is by saying, hey, if we do 4 minus 7, we get negative 3. I know negative exponents are going to be on the bottom, or you can think through and say big minus small, and put your variables wherever there are wherever exponent is try that again. Put your variables wherever the exponent is higher. So because there's 7 on the bottom, 4 on the top, there's going to be 3 left on the bottom. So that's one way you can think about it, is since there's more on the bottom than the top, they end up on the bottom. So a few different ways to think about this problem that all end up arriving at the same answer of 20 over k to the third. And if one of those or more of those was confusing to you, ignore those and go with the one that makes more sense. Number 5. Here we have this 2 outside this parenthesis, which comes before multiplication. And so I multiply this 2 to everything inside, to every exponent inside, I should say. And so 2/3 is currently raised to the first power. So this becomes 2 over 3 squared, r to the 4th, and s to the 14th, times 1/6 r to the 3rd s. Now, 2/3 to the second power is really 2/3 times 2/3, or 2 squared and 3 squared. So that's 4/9 r to the 4th, s to the 14th, times 1/6 r to the 3rd s. And now we actually go through and multiply. I can cross reduce 4 and 6 by 2 to give us 2 and 3. And that gives me 2 over 27 for my coefficients. And now for my variables, r to the 4th and r to the 3rd give me r to the 7th as we add those exponents. And s to the 14th and s give me s to the 15th as I add those exponents. Moving on to number 6 here. I have this all being raised to the power of -1. But first I want to check and say, okay, inside, sorry, this is quite grainy here. Inside, I can do some math here. And I could go ahead and apply this -1 to everything first, or my life's going to be a lot easier if I simplify first, rather than simplifying after applying this. So 14 divided by 7 is 2, and 12 minus 3, when we divide those bases, we subtract exponents, gives me w to the 9th. And this is raised to the -1st power. And so this means that both reciprocate. So you can think of this in 2 ways. You can either skip this next step I'm going to show in blue and jump to the end, or do this step in blue, where you multiply each exponent inside times the exponent of -1, getting 2 to the -1st, w to the -9th, which means that we reciprocate or flip both, leaving just a 1 on the top. There's never nothing on the top or bottom. It's always a 1 if you don't see anything there. Once again, you can just skip to this green step from the pink, saying, hey, this whole thing is raised to the power of -1, so it will reciprocate. Moving on to number 7 here. So 15 and 24 don't divide perfectly, but they do reduce by 3 to become 5 and 8. The x's and the y's, we have 2 ways to think about this. X's, 10 minus 12 is x to the power of -2nd. You could also think of it as, since there's more on the bottom, it'll end up on the bottom and call it an x to the positive second on the top, or excuse me, on the bottom right away. And then 4 minus 3 is y. If you do the approach where you call it a -2 to begin with for your exponent of x, then we do need to reciprocate that part where the 5 and y stay on the top, the 8 stays on the bottom, but only the x to the second moves, since that was the only thing that had a negative exponent. Personally, I jump straight to this answer by noting that 12 is bigger than 10, thus the variable and exponent will end up on the bottom. Number 8, I first need to deal with this exponent before multiplying. However, since this is inside parentheses, I can simplify there first, which I will. So I either call this 1 over c, or c to the -1st. Pick your poison. Let's just say I call it c to the -1st for now, and then I'll explain and show the other one as well. And I have to do this exponent as well. So -3 to the 4th and c to the 4th. -3 would be in parentheses there, so that is positive 81. C to the 4th. I'll go and showcase this, might as well. So -3 to the 4th, c to the 4th. And so this is c to the -4th times 81 c to the 4th. And as we add these exponents of c, when we multiply the bases, that gives us 0, which means we have 81c to the power of 0, which we know power of 0 just means this is 81 times 1, which is just, well, 81 and no c's, or just 81. Now, the other way we could have approached this off the get-go is that if we had called this 1 over c and raised that to the 4th, and then we still dealt with this in the exact same manner for the right hand part of this for the negative 3c quantity raised to the fourth. We would end up having 1 over c to the fourth times 81c to the fourth, which this is truly just the same thing as 81c to the fourth over c to the fourth. So you could have written it like this or this in this step, and I would choose the bottom one personally. And this ends up resulting in 81, as we mentioned. Moving on. It says to give an example of two monomials that when dividing have a quotient of negative 3n squared over m. So we need to give a problem essentially that reduces to this. So remember, this is not a monomial, but this is a quotient of monomials. Monomial divided by monomial, because a monomial doesn't have a variable in the denominator. So I need them to reduce to negative 3. So my coefficients are just something that reduces to negative 3. So I could do like negative 36 on the top, for example, and positive 12 on the bottom. That would reduce to negative 3. My m's, I need to have one more m on an exponent of that is one higher in the denominator than that of the numerator for my m's. So I could have like m to the fourth and m to the fifth, for example. That'd be 4 minus 5, which is negative 1, and would end up on the bottom. And n squared, same idea, but I need the exponent on the top n to be 2 higher than on the bottom n. So for example, I could do n to the 7th, n to the 5th. And this would reduce to that. So this is an example of which there are literally infinitely many possible examples. Let's talk about polynomials now. So the prefix poly just means many. So monomial, mono means one, polynomial means many. So many terms here. So it's the sum or difference of many monomials. So it's a bunch of individual monomials added or subtracted together. And the highest exponent of a monomial is called the degree. Similar to like the temperature is measured in degrees, that same degree, as far as spelling and pronunciation, all that. We don't use a degree symbol though, however, of that little tiny circle. Standard form. So we say a polynomial is in standard form when you are writing it, or I should say it's always right. So when you are writing in this manner, that I'll mention in a moment, you'll be using standard form for polynomial, which is how we always want them. Always write variables. Let me see if my pencil will choose to cooperate with me. Always write variables alphabetically. And put exponents in descending order. So those are two guidelines of alphabetical. I just said alphabetical instead of alphabetically. And descending order. So descending means greatest to least, such as 5, 4, 3, 2, down to 1, and 0. And alphabetically just means in order of our alphabet. A coming first, Z coming at the end. So we have some practice here on problems 10, 11, and 12 of putting these polynomials in standard form. So this number 10 here, we look for, since these are all the same variable of k, so we don't have to worry about alphabetical and one without a variable, we then just have to look at descending orders. Means for the exponents, we want to make sure the highest exponent comes first. So that's this. So this will be our first term. I'm going to put 1 underlined underneath that since that comes first. Then secondly, our next highest exponent is this negative 3k cubed. So I'm going to put 2 underlines since I'm going to put that second. And then third will come 1/4 k squared since that is our third highest exponent. So I'm putting 3 underlines so I know it comes third. And then fourth will be 8k to the fourth, or 8k to the first, And then last but not least will be -1. So you could put 5 underlines here, or if that gets confusing for you, you could put some other shape like a triangle to signify it's the last one, a square, or a circle, just to showcase that's over. So sometimes I do a triangle under my last one, just so that way I don't get confused with too many underlines. This underlining thing is not something you're required to do. It's just an organizational method to help some of us, and I highly encourage that you do it if you find yourself mixing up the order of any of these or losing track of a term or two as you start writing them. So first and foremost comes the negative k to the fifth. We take the negatives and positives and coefficients with the term. I'm going to lightly cross that out, showing that I use it. Then is -3k to the third, followed by a positive 1/4 k squared, followed by 8k, and last but not least is -1. And now this is in standard form. No worries about alphabetical, but it is descending order of the exponents of variables. On number 11, we do have to concern ourselves with alphabetical a little bit. So we look alphabetically here between all the ones that have A's. We just kind of go tunnel vision on A here when we have both A's and B's. So I'm only evaluating these three. This one can't possibly come first, this -b squared, because it doesn't even have an A, while some others do. And so now of those, regardless of whatever exponents of B there are here, we just want to look at saying, hey, which one has the highest exponent of A? And it's that one right there, 4a cubed. So that is what's going to come first here out of all of this. Then, as far as what comes second, we look for the next highest exponent of A, which is this one with A squared. And then third comes the third highest exponent of A, which is 7ab. And then last comes one without an A, which is just B squared. If ever there is a tie between two terms, so let's just say, for example, that this had AB, and these then were tied as far as A to the first and A to the first, we break that tie by going to the next variable. So in this case, if that was an AB squared, this would come third, and this one would come fourth, because the tie between the A to the first and A to the first is broken by the next variable. B squared comes before B, similar to how A squared comes before A. So, once again, 7ab though would come third, while -b squared comes fourth. So I have 4a cubed first, 18a squared b squared second, 7ab third, and then minus b squared last. On to number 12. As I notice that I have both x's and y's, I'm going to look exclusively at x's first before I move on to the y's, so I follow my alphabetical order, so I don't have to worry about any of these last two terms or any of the y's I see as far as organizing which one comes first. So that makes it a little bit easier to notice that this is my first term, second term, and third term. For x to the third, x to the second, x to the first. So let's go ahead and adjust accordingly. Or note that accordingly, I should say. And then after that, I have a y to the fourth and something without a y. So my tiebreaker goes to my next variable when I run out of x's. And so y to the fourth comes next, before the something without a variable, which always comes last. So now as I organize this, I have 9x cubed y first, minus x squared second, plus 5xy squared third, minus y to the fourth, plus 2. Now note, as we're going through this, we are never looking at the coefficients as far as what comes first or second. However, if there were ever two that were like terms, that had the same exact combinations of variables and exponents, then you would just combine those like terms and write your new coefficient in place of either of the previous two terms. Next, we're going to focus on classifying polynomials. So polynomials can be classified by degree, which is the highest exponent, as well as how many terms they have. And so we're going to fill in these charts to the left, the top one being for degree, highest exponent, and the bottom one being for the number of terms Which, remember, terms are these separated by plus or minus signs. So this one had 1, 2, 3, 4, 5 terms, for example. So for degree, 0 is what we call constant. 1 is linear. 2 is quadratic. Hopefully these look a little bit familiar as far as what we call these graphs, when you have like an x to the first and x squared. And then x to the third is cubic. X to the fourth is quartic. Think quarter. And cubic thinks a cube exists in 3 dimensions, or something being cubed is the third power. And then quintic. Quint is an abbreviation for 5, meaning 5, I should say. And so quintic is 5th degree. Now let's go over a number of terms. If it has 1 term, it is called a monomial, as we established, mono being 1. 2 terms is called a binomial, bi meaning 2, such as bicycle having 2 wheels. 3 is a trinomial, with like a triangle having 3 sides and 3 angles, or a tricycle having 3 wheels. And then 4 plus is just a blank term polynomial. So I leave that blank though, because you put whatever in that blank, however many terms that is. So let's say, for example, there's 5 terms. You call it a 5-term polynomial. If it's 20 terms, you call it a 20-term polynomial. So whatever number term polynomial that is. So up here for 13 through 18, we're supposed to be classifying these by what degree they have, as well as how many number of terms they have. So one from this category, while one from this category. And you should be looking to see if there's anything you can combine for like terms during these, because that would change the number of terms that we have. However, I will tell you on 13 through 18, there are none that need to be combined. So number 13, our highest exponent is this invisible 1. Highest exponent is exponents on a variable specifically. So this is linear, since it has a highest exponent of 1, or a degree of 1. And because there's 2 terms, it is a binomial. This highest exponent on number 14 is 5, so it is what we call quintic. And I should mention, if we were to get higher, such as 6th, 7th, 8th degrees, you just call it a 6th degree polynomial, a 7th degree polynomial, very similar to how we did with something term polynomial. Just call it that degree polynomial. And since there are 1, 2, 3 terms, it is a trinomial. (24) on number 15 has a highest exponent of 0 technically. This is x to the power of 0. And so this is constant, because remember we're saying highest exponent on a variable. And then this 1 term, so it's a monomial. And for it to be a constant, it has to be a monomial, but not all monomials are constant, which we'll see later. On number 16, the highest exponent is 3, and so this is cubic. And there are 4 terms there, so it's a 4-term polynomial. On number 17, our highest exponent is 2, so it's quadratic. And if these were not written in standard form, which they are, then you'd have to look for what the highest exponent is. But here, it's kind of given to you with the first term. And then there are 3 terms, so it's a trinomial. On number 18 here, it is 1 term only, assuming not before terms, though I have to go at highest exponent of 4, so degree of 4, which is quartic, quarters. And it is a monomial, which once again, as I mentioned earlier after number 15, is that all constant functions are monomials, but not all polynomials are constant. 19, give an example of a cubic binomial. So cubic means it has the highest degree of 3. So you could do just x to the third, or you could do a coefficient here if you want, such as 4. and then it has to have two terms, so we have to add or subtract something after this. So I could do plus 8, for example, or plus 8x squared, or minus 2x to the first, or something like that. And then on number 20, an example of a linear monomial. So one term monomial, but the highest exponent on the variable has to be 1. So this could just simply be x to the first. Or it could be 2x, or 3x, or 4x, or negative 8x, or whatever. Doesn't matter. Next, we're going to talk about adding and subtracting these polynomials. This is really just the combining like terms. That's all it is, and then we write our answer in standard form. So some of these polynomials are in standard form already, like in this first parenthesis, while this second parenthesis is not. So I'm going to go ahead and organize here with my underlines across each parenthesis. So if it comes first, x squared, comes second would be x to the first, and comes last or third is 4 and 13. I guess staying true to what I was saying earlier, I often do my last term is a triangle or something like that. I would do that here. Just to show I'm done. So combining 3 and positive 1 first would be 4x squared. Second is both negative 5 and positive 11x. So I get positive 6x as I combine those. And last is 4 and negative 13, which gives me negative 9. And so now I combine these. I added these polynomials while keeping it in standard form. Number 2, same idea. So as I organize this, I look for my highest exponent, which is 9n cubed. I don't have to worry about alphabeticals on this problem, but if there were different variables, I would be looking for that as well. Then n squared would come second, and that's these two. N to the first would come third, which is those two terms. And then last but not least, there are constants with no n's. And so as I go ahead and write this out, I have a 9n to the third alone as the first term. And then my second term is negative 4n squared and negative 2n squared, which gives me negative 6n squared. Quick reminder that we don't change the exponents when we add and subtract the bases. So then third is 2n and n. That gives us 3n. And negative 10 and 7 is negative 3. And that's our answer. Numbers 3 and 4 differ slightly in that it's subtraction. And so what we have to do is change this to addition and change every sign in the next parenthesis to the opposite. So if any of those were minus signs, which we'll see on number 4, then they'd become positive signs. So now I once again underline here. And so k to the third is first, k squared will come second, k to the third comes third, and, or excuse me, k to the first comes third, and the one without a k, just the constant, comes last. And so now as I write these, I get 5k to the third coming first, and then I have negative 2k squared and a negative 2k squared, making sure I note that negative. I get negative 4k squared. Positive 2k and a negative 2k give me no k at all, so I don't have to write plus 0k. I can just omit it or not write it at all, and move on to negative 17. I thought I undid that circle there. There we go. And that would be my answer. On to number 4 here. I'm once again going to go ahead and change the sign in every sign in the parenthesis that follows to the opposite. And I'm going to seek to underline. So y to the third comes first, y to the second would come next, y to the first comes third, oopsie, and then last but not least come our constants. So y to the third coming first, and then next would be 4 and negative 2 y squareds, which is positive 2y squared. And then next is 5y and y, and that would give me 6y. And last but not least is negative 3 and negative 1, which give me negative 4. Next, we're going to subtract this, the first parenthesis from the second parenthesis, which means this actually comes first. So it's really 8b squared plus ab minus 2a squared minus the next parenthesis, negative 10ab plus 7a squared minus b squared. And so I'm going to follow the same rules of thumb that I did in 3 and 4, where I change the subtraction to addition and make every sign of the following parenthesis the opposite. And now I simply reorder these. And so since I have multiple variables, I do alphabetical. So a squared would take precedence over a to the first, which takes precedence over those that have no a. So negative 2a squared and negative 7a squared are like terms, so they both come first. If one of them had like a negative 2a squared b, this would come first and this would come second, because those are no longer like terms. Then next would come my ab's, followed by those that just have b squared. And so now as I combine these, negative 2 minus 7, or negative 7 gives me negative 9a squared. 10ab and ab give me 11ab. And 8b squared and b squared give me 9b squared. And this is where we end 5.1 today. I know this says 5.2 at the top here, but that really starts down here. So with that being said, that wraps up Algebra 2, Section 5.1.